I'm Sonke. Hopefully most of you have seen me around. And I'm going to talk to you about dark energy and the fate of our universe. So I think I have quite an ambitious talk lined up. Because first of all, to understand the fate of our universe, we have to understand sort of what the universe is in the way that I view it as a cosmologist. And also then to understand what dark energy is, which isn't necessarily easy. And then to describe like why we can even make any predictions about the fate of our universe. Yeah, so that's roughly what I'm hoping to be able to do. Does anyone know what the difference is between dark matter and dark energy? Anyone brave? How do you?
Not brave enough to try, no.
Okay, well.
Dark energy, dark matter, that's like exploded.
Not that I know of. But it could be. It could be. Yeah.
Maybe that could be
There are interaction series, so yeah, you're not a million miles away.
So
it's good.
So dark energy expands the universe, right? It's the force expanding the universe.
Yeah, correct.
And dark matter, it's matter though.
Yep.
But it's compressing the universe in a sense?
Yeah, so dark matter has matter, and matter always attracts other matter. So dark matter is always pulling the universe together, and dark energy is sort of pushing it apart. Okay, cool. So I'll go over that in a little more detail in a minute. Okay. So the first thing I want to do, I should probably stand here. So I want to describe sort of the universe in my view as a cosmologist. Okay. So this is a little picture, like the classic zooming in and out. So we'll start with the Earth. Okay. Here we have the Earth. As a cosmologist, there's very little for me that I care about the Earth. I'm sorry to say. It's, obviously it's hugely important to all of us, but for cosmology in our models, like it barely enters. For astrophysics, it's more interesting because, of course, if we know about the Earth, we can know about other planets, et cetera, et cetera. But in general, like boring. Okay, let's move on. So the solar system is a little more interesting. It's a little bigger, so there's more stuff in it. So it might affect how the universe is modelable. But again, as a cosmologist, not so important. In terms of astrophysics, there's loads of cool things that happen. For example, ta-da, solar flares. So that's like a 2-scale picture of like the Earth and like a giant solar flare. So like a lot of interesting things happen there. But as a cosmologist, not so important to me. Okay. So then we go to a much bigger scale, which is now of like an entire galaxy. So do we think entire galaxies are important to a cosmologist? A little important, yes. So they're a little important. So before I describe why they're not important, I just wanted to sort of point out some interesting things in galaxies from an astrophysics point of view. So galaxies, first of all, come in different shapes and different styles. Most of them are like this boring style, rather than sort of this interesting spiral shape. Does anyone know the name of this galaxy?
Andromeda?
Nope. I think it's the Whirlpool galaxy. Yeah, but Andromeda is in here. It is there. That's Andromeda. So back in the day when they didn't have like photographs and like computers, people used to look through telescopes and like sketch them. And that's what someone sketched. I think it's what someone sketched. It might be a sketch today, but that's a sketch of this. Gesundheit. So like we now have like all these like marvelous images compared to this. Now we're like here. So we can look at cool things. So these are like cool galaxies. I have a hunch this is a galaxy that was collided into from another galaxy, and it just sort of like punched a hole through it. So you have like this ring. It's like kind of cool. Here we have colliding galaxies. I think they're called either like the mice or the tadpoles. And astrophysicists always like to name things. They're like colliding. Do we know about the Milky Way and Andromeda, our neighbor, that they're going to collide? Yes, they're going to collide. Potentially going to collide. So one day, people will look up the stars and they'll see like that in the sky, two galaxies colliding. If we're still around by then, no promises. So galaxies are important for dark matter, okay? And dark matter in turn is important for cosmology. So the reason it's important is because you can infer the existence of dark matter from galaxies, okay? And I'll just brush over how you do that. So you have this galaxy, and we all know, like, when a police car goes by, it goes like, Nina, 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 right? It goes and comes. Same thing with light. So the light, as it rotates towards us, is shifted in frequency, and away, it's shifted in another, like the opposite direction. I'm not going to say which in case I get it wrong, just playing it safe. So basically, from these rotations, you can infer the velocity of the stars, like sort of at each point in the galaxy. Okay? And when you do that, you can compare it to what you'd expect the velocity to be if you know what the mass is. Okay? So does anyone want to say like why the stars are rotating? It's because of gravity, right? So gravity is created by matter. So the more matter you have, the more rotation you would expect to have. Okay? So the sun, for example, like we rotate very rapidly around the sun compared to the moon rotating around the Earth. Okay? Because the sun is more massive, along with like distance and things. But generally, like more matter means more velocity. Now, if we add up all the stars that we see, we get this sort of calculated red curve of what the velocity is at every point in distance here. And when we measure it using the Nina effect, it's a technical term, we get this measured curve here. And we see it's like hugely different. Okay? So you might say, oh, maybe there's like a lot of gas that isn't in a star. But no, actually. That's one of the things that we mainly measure. It's like the, I think it's the IGN, intergalactic yeah, got it. Perfect. So we actually measure that, the gas. We take that into consideration. And most of the mass of the galaxy typically comes from the gas rather than the stars. Or it might be just, yeah, I'll just roll with that. Okay, so we count up all the gas and the stars, and we get this calculated curve. So we just infer that there must be other stuff there that we can't see. So what is something that we can't see? It's, dark. Ah, perfect. And it's heavy, so it's matter. Ah, dark matter. Okay, so that's all dark matter is. It's stuff that we know is there. We can see its gravitational effect, yeah, on the pulling of these stars as they rotate, but we have no way of detecting it because it doesn't interact with light. Okay, so that's dark matter. And dark matter is important for cosmology, as we'll see a little later. But before we go into that, I just wanted to test your, I want to just like show you some pretty pictures, because that's what astrophysics is good for. So does anyone know what this nebula is called? Close. I think it's the butterfly nebula. I think so. It's a little pretty butterfly. Does anyone know what that is? The name is kind of there. It's a freebie. So Cat's Eye Nebula. Does anyone know this one? I think it's a rainbow galaxy. I think it is. I might be wrong. I didn't Google it beforehand. Anyone this? This is like my favorite, I think. Huh?
Looks like a dandelion.
Dandelion? Good. I think it looks more like a slice of a fruit.
Kiwi.
A kiwi. maybe.
Great.
I think they named it the lemon slice nebula.
I didn't know that like quite a specific name.
Yeah. Yeah. Oh, good question. So a nebula is typically, when a star explodes, like it gives off a lot of, like it's the stuff that made it up. So it explodes and all the gas sort of expands outwards. So you can see it like really clearly, for example, here. So you can see sort of this jet of explosion and all the gas is like pushed out. And like you have several different explosions and it creates these ring effects. And then it's obviously giving a lot of energy off still in the middle. So all that energy, it sort of moves through and bumps into the matter and the gas. And when it does that, it sort of scatters off it and like lights it up, like heats it up, and then you can see the light coming off it. Like I don't think these are true light images. I think they might be like altered a little so that the frequency that you see is more visible. But in general, like a nebula is like an explosion of gas. And some galaxies are just like collections of gas. So in like star-forming regions where like stars are being born, like all the gas comes together and at some point it gets dense enough to form stars, but those also are nebulae. Okay, so, and finish, oh, so this one, yeah. What do you think this one is?
Brain.
It's good. I think heart. Heart's actually good, isn't it? If they like made it red tint, that would be probably a better name for it. It's the Eskimo nebula. So this is like the little Parker, like the, yeah. Yeah. And then this one I think was discovered actually by an amateur astronomer, like fairly recently, maybe like 20 years ago or so. Anyone want to take a guess what that looks like? Like if you, yes, soap. So this is, I think they call it the soap bubble nebula. It's like it's really weird, but it's pretty pretty. So yeah, so these are lots of things inside galaxies. Some other cool things inside galaxies. Just because I think this is awesome, is called exoplanets, so just the study of other planets and other solar systems. And what we look for is we look for this sort of Goldilocks zone, which is a habitable zone. So it's when the planet that we find is sort of far away enough from the Earth not to have all the water in steam, but not so far that it's all frozen. Yeah? The idea is you have like liquid water on it, and the idea is that maybe there could be life on those planets. It's like, isn't that cool? So they look for that. I have a friend who looks for these. So I think when she does it, she models, so they get like basically a thing of light from the star, and they wait for the planet to move across it. So you get like a dip in the like intensity of the light, and then they model like certain things. And their model has maybe 5 parameters if there's like 1 or 2 planets there, and then like 6 or 7 parameters. And these 3 parameters are like the rotation of the rate of rotation, like the mass of the sun, the mass of the planets, all of these things. So then like people are able to model this. Okay, so I'm saying this to set you up for a question later about cosmology and modeling cosmology. Okay. So remember, there's about 5, maybe up to 10 parameters maximum in like a solar system. Okay. So that's all galaxy stuff, and from galaxy stuff we can infer dark matter needs to exist. But again, it's not that significant to know the physics of galaxies. So like, you know, if someone could model a nebulae, like great, but you know, I don't care. So it's not gonna it's not gonna help me get my PhD or papers. Okay. So then we move on to the next scale, and now this is like the cluster of galaxy scale. So at this scale, loads of weird things start happening, and you get some cool things that point again to dark matter existing. So one of these is called gravitational lensing. I won't go into huge detail, but basically there's like this heavy spot here, and the light is literally bent around it. Yeah, this is something that like Einstein hypothesized, and actually the detection of this was what proved Einstein's theory correct in the first place. So it's pretty cool. I just wanted to show you like a picture that this really does happen. Like, can you see sort of the bending of light maybe? Sort of like these smearing effects. So like these galaxies aren't like weird, like long stringy things. They're just smeared by like this huge clump of matter that is there. And a really clear one, if you doubt me now, like, ta-da. Like, that's just one bit of mass here, like the whole galaxy is like swirled around it. Like the galaxy is far behind it, the light gets like pulled around it. You get this really cool effect. And again, if we count all the gas and all the stars that we see in the mass, typically it's not heavy enough to create the lensing effect. So you say, oh, there needs to be some more stuff that we can't see, more dark matter.
Wait, so is that
Yeah.
the light of a galaxy coming from behind?
Yeah, sorry. So this one is behind,
Yeah.
and this one is like the heavy
Is that
thing.
a galaxy in front?
I'm not entirely sure. I have a hunch it probably would be. It'd have to be something heavy.
This may be a stupid question, but I mean,
Yeah.
light is massless, so why is it being bent by the gravitational
That's a
pull?
beautiful question. So we're going to cover that a little bit in a minute when we get to like Einstein's field equation of general relativity. So we'll get to that. Welcome. It's okay. Okay, so gravitational lensing. So another cool thing, so I won't go into too much detail, but I just wanted to show you this. Like this is like a really awesome way of finding dark matter. So like this is a cluster of galaxies and a cluster of galaxies. They've collided. Most of the stars just go through each other because like there's not actually much like probability of colliding. So they just sort of disperse. And all the gas does collide and it goes in the middle. So all the pink stuff is highlighting the gas, and all the blue area is highlighting where most of the mass is. But we know that the gas is heavier than the stars, so it's not that like, oh, these stars are really heavy. Again, there must be something else which we can't see. Again, more. Yeah. Yeah, so like loads of proofs for dark matter, like that just suggestions that we need them. And here's another one. This is more important now for cosmology. Okay, so this is called large-scale structure formation. And in general, so remember I said, or someone at the beginning mentioned that gravity always pulls together. Okay, so what happens if you have like this, just a lot of gas, and you give it, 1 billion years, then it'll start pulling itself inwards. And another 1 billion years or so, and you get these sort of spindly fingers starting to get created. This is called large-scale structure. And this process, if you observe it, so like you can look into the sky, and you know that when you look at a star that's further away, like you look back in time, because obviously the light had to travel to you. So like if it's 10 meters away, light only traveled for a little bit, if it's like 1 billion meters away, it would have taken a little longer to get to you. So you can look back in time and you can actually see this process happening, basically. And if you calculate all the physics involved, again, you just find that if all the stuff is there that is gas and stars, that's everything, you wouldn't have the gravitational pull to create this structure formation. So again, more dark matter proof.
Is that something that people can model?
Yeah, so this is actually the Millennium simulation. Perfectly, you said that actually. So in this simulation, they modeled, I think, maybe like 10 billion particles in like a box, and then just like evolved those through time, and they created this like the actual simulation. So this isn't observational, this is computer simulated, yeah. So in this model, you need like, 10 billion parameters compared to our little solar system. How many was in the solar system, do we all remember? Couple, yeah, five to 7, so like 5 to 10. Here's like billions of parameters that you need to model this. Okay. So then, okay, so that's all good. So we're getting into the realm of cosmology. So, what actually is cosmology now? So cosmology is everything, okay? So the red box around everything, modeled as like one complete system, yeah? And for that system, you're after essentially only statistical effects, yeah? So, like I said, I didn't care about what a galaxy looked like, because I just care about like how many galaxies there are, just like a statistical measure of it. So how do we model a whole universe? It's the obvious question. So before we can talk about dark energy and how it affects the fate of our universe, we need to understand how we model a universe. So we can't observe all of it. Do you know that if you look out, you can't see all of the universe? Because some of it is more than the time of the universe away for the light to have traveled. Does that make sense? The universe is 1 billion years old. Light can only have traveled 1 billion light years. Yeah? And if there's something beyond it, it won't have been able to travel to us yet. Yeah? So we can't actually see all of it. So we have to make assumptions about it. And we have lots of little assumptions, and we have lots of laws of physics. Okay? And this is Einstein's field equation of general relativity that I want to show you. Has anyone seen it before? Yeah. Yeah. Is it a difficult equation or? It's easy. Ta-da! There we go. That's like Einstein's general relativity. Looks simple? It's like really horrible. So I'll give you the terms. So this was called G mu nu, is the effect on space-time. So in Einstein's theory, space and time are sort of one thing. So it's 4-dimensional, 3 spatial dimensions, 1 time dimension. We'll see a little bit more how that like manifests itself in a second. But basically, this is the effect on space-time. It's the curvature. Yeah. So the curvature of space-time is equal to this little kappa. It's just a number. Like I could have just left it out, but I thought I'd show you the full Einstein equation. In its full glory. So it's just a number, and this T mu nu is just a description of the stuff in the universe. Okay. So it just says the curvature of space-time is essentially equal to the stuff in the universe. So remember, we saw like the light bending. So it looked like there was some curvature to the path of the light. That's not because the light is bending, because it has no mass. It's not like moved by the force of gravity, but it moves along bent space-time. Okay? And it's bent because there was like just a ton of stuff, a ton of matter. Okay? And also matter and energy is sort of equivalent. Yeah? So light, you can measure it in the same sort of scale as you can measure like tables and everything. And you guys as well. Although in my models, like, you guys aren't in my models. Sorry to say. Not enough of us. So, okay, so that's this equation. And this is sort of like a clearer picture of what it is. So imagine you have a lot of mass here, and you get a lot of curvature. This is like a 2-dimensional like bit of space. And this is typically how people like show you this in real life. So they like get this rubber membrane, and they put something heavy in the middle, and then they like throw little balls around. You can see that like orbit. That's sort of like a good description. Except for this is happening not in 2 dimensions as they are, but in like 3 dimensions, and actually space as well. So like when you start going close to a black hole, like weird things happen with like how like people see you. They see you like moving in slow motion, and it's like lots of weird things happen because time itself is bent as well. So this is again just looking at the other effect. So you can see the little beam of light is being bent by that, yeah, etc., etc. So we have our physics. Now let's state our assumption. So to solve that Einstein equation, which looks simple, but like it's really not, it's horrible. You can't just solve it. You need to work with certain models. So for example, when people model like black holes, they'll use a specific assumption about like spherical symmetry, and they'll be able to solve it based on that. So we use the cosmological principle, which is that everything sort of looks the same on large scales. So you remember how you saw that Millennium simulation where it was like there, sort of looked like there were bits that were like had more matter, like more bright. When you get to like the really large scale, you know, you can imagine that box was like a little tiny thing there. And the whole thing actually looks pretty flat. So whether I look that way, it's just the same everywhere. And that symmetry essentially allows you to solve it, and you get this. This is the second and last equation, I believe, of the talk. Does it look okay? Is it like a handleable equation? Sort of can make sense of it. So this little ds, like we'll ignore all the squareds. Like this ds is just space-time. Space-time is made of a little bit of dt, which is a little bit of time. And this is just a constant. And then and then a little bit of space. So this d chi is sort of the shape of space. So you know, people might say that the universe is like round or it's flat. That's captured by this. And then this little a, which is a function of time. Yeah? So space-time is a little bit of time and a little bit of space, and a little bit of space can get bigger or smaller depending on the time that we are at in the universe. Yeah? So does that make sense? Yeah, not too bad, right? Einstein, it all sounds very scary, but you know, it's all right. We can manage it. So this is the sort of picture you get. You know, typically, the universe is a balloon and like expands. Yeah. Note that if you draw little galaxies here, then at times, like depending on like how the structure is formed, like these galaxies will stick together even if the universe is expanding. Yeah. So the universe is expanding right now, but it doesn't mean that we're going to like move away from each other necessarily. Okay, because we're attracted by gravity, and these galaxies are attracted strongly enough by gravity to not be affected by this expansion. Okay, they're gravitationally bound systems. Okay, so that's important in a little while because we'll find out that there could be cases where the universe expands too fast and things aren't bound anymore. It's a bit crazy. Okay, so we have our general relativity. We have our little solution, and then we can start looking at the universe. And the easiest thing to do is look at the past. So if you imagine this as the size of the universe, we observe, oh, actually in the past it was a little bit smaller. And then if we keep looking back and extrapolate back beyond the point at which we can't look back anymore, we conclude that at some point it must have been zero. Yeah, so then obviously if you start here and accelerate it forwards, well, it's like a big explosion, right? So does anyone know what this is called? Yay! Full marks. So that's the Big Bang, okay? That's basically what it is. So it comes out of that equation that we saw, where the scale factor, the a of t, is changing with time. Okay, so now we can ask what is the history and the future of the universe. So they all start out here. So we have three potential histories based on if there's only matter. Okay, so at present we're sort of here, and you see they all look the same. And we all started from this Big Bang. Now, one thing that can happen is that there's so much matter that it just pulls the universe back together and whoop, it recollapses. Does anyone know what this theory is called?
Big crunch.
Yeah, spot on. So this is a big crunch for obvious reasons, okay? So if there's so much matter in the universe that it just pulls the universe itself back in, because remember, space-time is related to like the matter and like the curvature, so it can literally pull it back together, get a big crunch. This is what Einstein wanted. So he was really hoping that the universe would be this critical universe where it's sort of, you start with a Big Bang, and then there's just enough matter to sort of slowly ease you into like an eternal existence of the sameness. Yeah? And that is it's sort of like asymptotic, so it like keeps expanding, but just a little tiny bit less than the last time. And just it never really slows down, like it never like collapses again, and it never moves further apart. So that's a nice universe. Okay. So let's hope that our future universe looks like this, right? So this is a coasting universe, which is just that there's not much matter, and the universe just expands as if there wasn't any matter, because there's nothing to pull it back together. And this typically what will happen in that universe is like stars, like our sun, at some point will explode, and all the gas will like form a nebula. But that nebula might be too far removed from all the other nebulae, and like the gas will never combine again to be like sufficiently dense. And like essentially everything gets very cold and like boring. Yeah, so it's like the big freeze. Although the big freeze might be like the latter one, but I'm going to call this one the big freeze for simplicity. Okay, so those are our universes. Incidentally, how many parameters do you think we need to model our entire universe? Anyone want to take a guess? 5 to 10? Why would you say that? That's like spot on. Why would you say that? I was hoping someone would be like, well, the Millennium Simulation was like billions. No, it's 6. Like the best model we have is 6. Why did you say 5 to 10? Oh, did I tell you already? Or no, did you talk with someone else?
No, you.
Someone, did I?
You said to remember, so I'm trying to remember.
No, I meant for the whole, the whole cosmology, not for the solar system. So the solar system is 5 to 10.
A lot more. I'm sorry.
That was meant to be like my big fun moment where it's like, only 6? Wow. Yeah. But basically, so like when they make these models, like remember, like the Millennium Simulation is modeling like all the stars in the galaxies, so it needs a lot of things. But we don't care about those, so you just get actually only about 6 parameters that you need. Like 2 of those are just for this period, and 2 more basically say how much like matter there is and how much dark matter, and then 2 more are related to sort of like this time difference there. It's actually really simple. Okay, so now we have some theories. Okay, now let's test it against observations. Okay, so it's not, being a theorist is fun, but it's not everything. So we ask, what is the fate of our universe? Okay, so superheroes all over the world, would be wanting to know this answer. So we observe, and we observe specifically these, which are type Ia supernovae. Okay, and we observe something sort of unexpected. And just for a little bit of background, because these are like really important for cosmology and dark energy. These supernovae, essentially, it's when you have sort of like 2 stars, and this one basically like sort of steals away from this one. So this could be like a neutron star, so it's like already collapsed or something. It's like really dense, sort of stealing from this one, and it keeps stealing until it explodes. And because like all these exist all over the universe, and they all sort of accrete in the same way. They all explode at the same point in time, or like in mass essentially. So we know exactly what the physics are of that explosion. Yeah. So like, for example, if this star exploded, we wouldn't have known how much matter or mass there was in it to begin with. But with this one, we know it has to explode once it gets up to like the critical point. So we can use these as what are called standard candles. Okay. So if one goes off there or there or there, we can look at the light that arrives to us, and that will tell us like how far it's traveled, like what has happened to the light in between, like the journey and everything like that. So they're really useful. And it was maybe 20 years ago that people like observed these and basically discovered that something very weird was happening. And they've already got the Nobel Prize for this, even though it's like really recent in terms of Nobel Prize history. And what they realized is that the universe is actually accelerating its expansion. Yeah. So none of this like matter pulling together. Like no. Like it's totally the opposite. Okay. Feel free to say woo. Like so then we get like these sort of. We actually have a 4th scenario, and this is actually probably what's happening. And what's happening here, so there's 2 things that could happen. One is similar to like the big freeze, where things just move far apart. And one is a lot more dramatic, shall we say. So depending on how dark energy manifests itself, it could be that this acceleration is essentially exponential. So at some point, remember in the balloon before, I said that the galaxy holds itself together? Well, at some point, you're blowing that balloon up so much. Like imagine you put some water or like some ketchup or something on the balloon. If you blow it up slowly, it'll like pull itself together, right? If you do it really fast, you can imagine it like spreads out across the balloon. And the same thing would happen with galaxies. Like it would accelerate so fast that the gravity is not strong enough to hold the galaxy together. But then in the solar system itself, like the Earth is only attracted by gravity. Yeah. So at some point, because it's an exponential process, they would also get torn apart. And then I'm standing on the Earth because of gravity. It's like, uh-oh. So I'd get pulled apart too. And then actually, like it's not gravity in my fingers, but it is a force, and there's space separating between those two. And space is just expanding exponentially fast. At some point, like my whole body will just like explode. Okay, so this is called the Big Rip. Yeah, and it's like certainly it's certainly far removed from the Einstein's ideal scenario. So we're kind of deciding whether it's sort of the big freeze version of this or the big rip version of it. That's where we're at the moment. So now, this is actually where the talk starts getting about dark energy, okay? Because, you ask the question, why is this acceleration happening? Okay, so before there was matter, there was dark matter, that's all there could be, okay? It has to pull itself together. But now we say that actually there's a new force which is just pushing itself, like pushing away. So the universe is being acted essentially oppositely to gravity to this. And, we can't see it, let's call it dark, and, it's the T mu nu thing, so it's like a matter-energy thing, so we just call it energy. Matter's already taken, so dark energy. I'm not sure if there's a better historic interpretation of why they called it that, but that's how I think about it. So we call this dark energy. And you can ask the question now, how much of this dark energy is there, okay? So we know that if there's a lot of matter, it pulls itself in. And we can quantify that and we can observe that in the universe. So we can do the same with how much push there is, okay? And you get this, so it's a little outdated, but you basically get this. And it's not such good news if you're a cosmologist. So you have this model of the universe, and then you discover that, okay, we understand like solar systems, and all of the matter that we've ever seen is only 5% of the universe. It's like, oh great, so like 25% is like this other stuff that I've got no idea about, I just know it has to exist. And then suddenly like this 70% is not even on the scale of like matter. So like we just turned out we just don't know very much about the universe at all, okay? So, but we can do a little better than that. So we don't know much, but we know a little bit. And we can sort of start answering the question of what is dark energy. So it's in a way the field is in its infancy still. Like we're not able to make strong conclusions because the data is lacking. But I'll just sort of outline some principles in it. Okay, so dark energy, like very basically, it's an energy component that makes the universe expand. Okay, our best guesses are that it's something called a cosmological constant, and this is basically this. So remember we had Einstein's equation. You can basically just add this in for free without changing the physics, like without changing the equality rather, but it sort of gives you some new physics that could create this. So okay, cool, yeah, let's add it in. Like we have no reason to as such, but yeah, like let's just add it in because it works with what we see. So it's just a thing you can add in. Equivalently, you can add it into the other side, and it still works. In that case, obviously, it would be a minus, but yeah, whatever. So you can add it in either side that you want. And if you do it on this side, you actually get sort of a physical interpretation of it, because here it's on the curvature of space-time side, but here it's actually a matter element, right? So you can ask yourself, okay, so if it's here, like what is this energy component? And we get what's called the energy density of the vacuum, okay? And you can compare it to quantum mechanics. So don't worry too much about like how you do it, but basically you get an incredibly wrong prediction, okay? And it's really, really sad. It's wrong by that number, which I wrote out for you. So you can just see so that's how many, you have to multiply it by that number to get what quantum mechanics tells you. So it's pretty bad. So we thought we had an idea about what dark energy was, and then we tried some math, and it turned out we didn't at all. It's like the story of dark energy. Another approach is to define what's like a quintessence. You have like a Fifth force. That's what quintessence means. It's just something with negative pressure, and like you can kind of do stuff with it. It basically allows you like a more flexible approach, other than just saying that it is like this vacuum energy. I won't dwell into it too much. You can ask me afterwards if you want. Another thing is to modify general relativity itself. So like Einstein could be wrong. I'm not going to bet on it, but he could be wrong. So here's a cat demonstrating gravity is just a theory. He's obviously floating. So, we should have seen it coming, really, that there's something amiss with gravity. There's like people working on this. I wish I could say that was my daughter sort of working on that. But yeah, so you can modify gravity. But at the moment, we have a lot of theories, but insufficient data to decide between them. And just because I was going to show you something that I actually did, so that I can say that this is my research, I was going to show you that the way that we're currently investigating it is looking at this function. So W of Z is what we call it. And W is basically how negative the pressure is. Okay? So you have a little bit of this stuff, and then if W is very negative, then it pushes apart a lot. If it's not so negative, then it pushes apart only a little bit. And we get these results. Ta-da! Very pretty. So the model that I told you before, which is like the vacuum dark energy model, is basically like along here. Yeah, is this line W is -1, and it doesn't matter. So Z is the time looking back at the history of the universe. Yeah. So for lambda CDM, so the model saying that we have this constant on the matter side of things, like it would predict this. And then when we look at the data, we get that it's pretty much spot on that. So like the darker region is like the more favored region of what we expect based on the data, the outcome to be. So it's like, okay, we know that it can't really be that based on our theories because quantum mechanics disagrees, but like the data is like really pushing us towards this. So, you know, like we're just in trouble at the moment. It's just in trouble. So yeah, so that's basically the end of the talk. So the conclusion to take away is just that dark energy is something. It makes up most of the universe, and it's just needed to explain the acceleration that we observe. But aside from that, you know, we're pretty up in the air about what it could be. Thank you.